Hello and welcome to AP Physics Virtual Kitchen Edition. Today what we're going to do is I'm going to do some sample problems dealing with series and parallel circuits. Hopefully you have watched the presentation that I posted. It's not just a PowerPoint anymore. There's actually me talking, and it's short. It just gives you the rules for series and parallel circuits. You've had practice now drawing the circuits, and now we're going to find information about those circuits. So on the PowerPoint slide, there were these rules. And I would advise you to write these down as you're trying to do these problems, and you can keep referring to the rules. The math is easy. We're just going to be using Ohm's law, which we're going to get to in a minute. But these are the rules for series and parallel. The three things that we're worried about, as I've stated before, is voltage, resistance, and current. And so in a series circuit, which, to refresh your memory, is one component after another, we have that the voltage is going to add up. So what that means is if you have a 9-volt battery, across each one of the components, you're going to have a voltage drop. And those will add back up to whatever the battery is. The resistance, the resistance for the entire circuit, it's easy to figure out. You just add up all the resistors. That's called the equivalent resistance. That's why there's little EQs down here. Some books will put total, they'll put TOT, or they'll put B for battery because this is the voltage, but I don't like that. I usually use equivalent. That's what your book uses. The other thing that's true about the series circuit is that the current is the same through every portion. The current is the same through every part, every component that you hook up. That's why there's a plus sign with the dot, dot, dots, because you could have more than two. Parallel is different. In a parallel circuit, what you're going to have is the voltage will be constant through all of it. So the potential difference across each one of the components will be the same. So if it's a 9-volt battery, there's going to be a 9-volt potential difference across each one of the components. The resistance is a little bit harder to figure out. It's called a reciprocal resistance. So the total resistance for the entire circuit will be equal to the addition of each one of the reciprocals of each one of the resistors. And I'm going to do an example problem like this. And then the current adds up. So the three things we're worried about: voltage, resistance, and current. And the reason that we're worried about that is because we're going to use those rules and Ohm's law. Now, Ohm's law says that the voltage is equal to the current multiplied by the resistance. The thing that makes this more difficult than what we've done in the past is you have to make a definition for this. So like if you're talking about the entire circuit, then all of these have to be for the entire circuit. This has to be the equivalent current, this has to be the equivalent resistance, and then you can use this equation. If you're talking about one particular resistor, then this is the voltage drop across that resistor, this is the current going through that resistor, and this is the resistance of that resistor. So you can only use this equation for particular parts or for the whole thing, but you can't mix and match things. So we're going to start out doing easier ones. The two worksheets that I've uploaded for you to do that'll be due next Tuesday, they're fairly simple. It's to get you used to using the rules and using Ohm's law. So at this time, I'm going to do two problems, one series and one parallel. And so we're going to keep, I don't know, can you see that? Not this. We're going to use three resistors, a 10, a 20, and a 35 ohm resistor, and we're going to connect it to a 12-volt battery, and we're just going to use the same information for a series circuit and for a parallel circuit, and we're going to try to figure out everything we can about each part of the circuit. So the first thing I'm going to do is I'm going to draw the circuit in series. So I've got a battery, and I've got 1, 2, 3 resistors. So this is 12 volts across the entire circuit. And then we'll call this one R1, this is R2, and this is R3. And so there's a lot of things I can figure out. I can get the equivalent voltage, the equivalent current, and the equivalent resistance. I can get the current through 1, the resistance through 1, the voltage through 1. The same thing for 2 and 3. I can figure out all of this information by using Ohm's law and the rules. The first thing that you should do is figure out the equivalent resistance. The equivalent voltage is what the battery is doing. That's the 12 volts. The equivalent resistance for a series circuit, you just add them all up. So the equivalent resistance is equal to R1 plus R2 plus R3. And I said that these were 10 ohms and 20 ohms and 35 ohms. Okay, so honestly, 10 plus 20 plus 35, so we have an equivalent resistance of 65 ohms. Now, notice how I'm putting the subscript equivalent on that. That's because I can now only use this 65 ohms with other things in Ohm's law that also have a subscript of the equivalent. So V equivalent, that's the voltage, that's the battery, that's 12 volts. Well, now I know R and I know V, so I can use Ohm's law and figure out the current that is going through the entire circuit. I just take 12 and I divide it by 65. I don't know what that is, but I can use my calculator and I get 0.18. So the amperage, because that's what it's measured in, and I put that on, see, V stands for voltage, it's measured in volts, that's the symbol for a volt. Current measured in amperes, capital A. R resistance ohm, we use the omega because we can't use an O because it looks like a zero. So, well, what did this tell me? It told me the resistance in the entire circuit. I figured out the voltage because it told me the battery. And then that's the current in the entire circuit. But then I can remember that in a series circuit, and this is a series circuit, I can now figure out what I1, I2, and I3 is because it's all the same. So if I were to wire in a multimeter and find the current, it's going to be the same for all of them. It's going to be the same for all of them. So that's the 0.18. But the voltage drop across each one, if I were to take my multimeter and set it for voltage and put it across each one of these resistors, that would be different. It's not going to be the 12 volts. It's going to add up to the 12 volts. So how do I figure that out? Ohm's law again. Use Ohm's law. Just use it like this. The voltage across the first resistor is going to equal to the current, which is that 0.18, times the resistance, 10. So the voltage across one is 1.8 volts. That's the voltage drop across the first resistor. Do the same thing for the second one. Voltage drop across the second one is I2 times the resistance, 2. Notice they all have the same subscript, but current's the same, 0.18 amps times 20. That's probably 3.6. And that's going to be volts. And then do the same thing for 3. And then there's a check at the end we can do. So this is going to be the I3 times R3. So 0.18 times 35. Can't do that one in my head. 0.18 times 35 is 6.3. Now, here's the beauty of this. The rule says that all of these potential differences across each one of the loads has to add up to the battery. So if I take 1.8 and 3.6 and 6.3, I get 11.7. That's close enough. I did some rounding up here, and that's why I didn't get an exact answer. But that's what it is, 11.7. So it worked out. And that's how you do the series circuit ones. You can find out everything, or you could be asked for just something specific. Maybe they just want the voltage drop across R1, or maybe they just want the voltage drop across R3, or they want the circuit's current. Doesn't matter. This is how you can find everything that they could possibly ask you for about a series circuit. Now what we're going to do is the exact same thing, but I'm going to put everything in parallel. And of course this is going to be a little bit different because we have this reciprocal function, which means fractions, and we all know how much we love fractions. So battery, same battery, 12 volts. But now 1, 2, 3. R1, R2, R3. But this I'm going to keep them the same. 10 ohms, 20 ohms, 35 ohms. Okay? The first thing we always try to figure out is the equivalent resistance. The equivalent resistance in a parallel circuit looks like this. 1 over the entire resistance is equal to 1 over R1 plus 1 over R2, in this case 1 over R3. If there were 5 resistors, we would do all 5. And then what I do on my calculator, I just use my x to the -1 key. So I put 10 to the -1 plus 20, reciprocate, plus 35, reciprocate, and then I hit enter, and it gives me that weirdness, but I have to remember that that is the reciprocal of the answer. So then I just hit the x to the -1 key again, and I get 5.6. So the equivalent resistance is 5.6 volts. No, I'm sorry, ohms. So just as a quick reminder, on the last one when we did this, when you put them all in series, the maximum or the equivalent resistance was 65. When you put them in parallel, a lot less resistance having things in parallel. So that's the equivalent resistance. Now, I follow the rules for parallel. Whatever the battery is going to be the potential difference across each one. So that means each one of those is 12 volts. 12 volts here, 12 volts there, 12 volts there. Now I can figure out the current through each one because the current is going to be different. The current through I1, using Ohm's law again, the current is going to be equal to the voltage divided by the resistance, but you have to make sure that they all have the same subscript. So the voltage is the same through everything. That's going to be 12 volts. R1 is 10 ohms. So this is going to be 1.2 amps. I2, same deal. V is the same. 12 volts divided by the 20 ohms. That's going to be 0.6, right? Let's try. Oh, look, 0.6. That's going to be amp. So 1.2 is the current going through this one, and 0.6 is going through that one. Do the same thing for I3. I3 is going to be 12 volts divided by 35 ohms, 0.34. And then just like we did the check with the voltage on the series circuit, you can do the same thing here. So I'm going to take 1.2 plus 0.6 plus 0.34, and I am going to get a total current of 2.14. That's what it should be. And that's one way of getting the equivalent current, or I can figure out doing that. So I take the 12 volts, this is getting messy, divide it by the 5.6 ohms, and I still get 2.14. So it's 2.14 either way. The equivalent current, 2.14 amps. Either add these all up or do Ohm's law and just make sure you keep your subscripts the same. So there are ways, and we'll talk about this more, I think, next week, more complex circuits where you have a combination of the series and the parallel. But I'd like for you to practice the series and the parallel. So there are two worksheets that are on these two. They're on Schoology. If you could just finish them by next Tuesday. If you have any questions, let me know. Email me. And if you think that you'd like to do a Zoom meeting or a Google Meets, we could do that too. Either way. And I can help you individually, or you can just send me notes and I'll help you individually. I appreciate all the hard work you're doing. And I hope you have a good week.